Rohan, can you check if the sound is okay? All right, we're gonna get started. Hi there, everybody. My name is Alvin Wong, and I'm going to be lecturing today, ML Mondays lecture number 1, and we're going to be talking about our review of AI and ML fundamentals from our lectures last semester. So make sure to sign in if you haven't already, and we'll get started after you guys sign in. Let's get started. So, like I said, I'm the education lead of GatorAI. I'm also assisted by 3 other ML lecturers who could not make it today, unfortunately. But you will see them around. If you guys show up to the next lectures, they will be lecturing along with me. And I'm very grateful to have their assistance. All right, so let's get started. Some administrative information before we actually delve into the content. All of our slides to our lectures will be uploaded to our Google Drive in our link tree, so you can access the slides. The recordings will be uploaded on YouTube on our link tree, so if you want to watch the recording again, you can also go to our link tree and then go to our YouTube. We have gotten some feedback from last semester for the ML Mondays on the difficulty of the concepts. And obviously we try to be as beginner friendly as possible, but it's very common that new concepts and material will kind of be coming along throughout this lecture. And we will try to explain most of the prerequisite knowledge as we go through the lectures. So yeah, just make sure you keep that in mind. Of course, questions are always welcome. Just raise your hand and we'll get to you as soon as we can. And always feel free to look up the material on your own and try to understand it yourself. That's really where a lot of the learning also happens. We also have a feedback question, so if any of you guys have feedback after this lecture, feel free to do that. Additionally, this is a review of past semester's lectures, so if you guys haven't gone to the past semester's lectures, some of this material may be pretty new for you, but that's okay. I encourage you to come next lecture, because next lecture we will be going through everything bit by bit. So this is just to kind of go over the conceptual understanding of machine learning. Right. So introductions. So this is obviously a lecture series covering beginner machine learning concepts. The focus for this semester is on applied knowledge, right, with a focus on deep learning and neural networks. So we're going to learn how to implement these models, besides just the conceptual information, which was covered last semester. So you can see kind of an overview of our plan of our lectures for this semester, and we will have more lectures planned as we go about, but this just gives you an idea of what we're going for. If you want to reach out to us, please do on Discord, email, or Instagram. We'll be happy to answer any of your questions on there. And of course, like I said before, all of our information is on our link tree. All right. So what is, first of all, artificial intelligence, right? We want to define artificial intelligence and machine learning as best as we can. So artificial intelligence, we're going to define it as the theory and development of computer systems able to perform tasks that normally require human intelligence here, right? So there's a lot of things that have been classified as artificial intelligence, such as visual perception, decision making, and speech recognition, right? Those are things many people would commonly consider to be artificial intelligence. What I want you to consider and think about is what are tasks that normally require human intelligence, right? Things that require human intelligence, there's a lot of things that require human intelligence, right? And some things still require human intelligence, and they're not really considered to be AI anymore, right? And so this brings us to the AI effect, right? It's a phenomenon where basically the definition of AI, or the concept of what it takes to be intelligent, is adjusted to exclude systems that have been normalized, right? So for example, in the past, path finding was considered to be artificial intelligence. Things like Dijkstra's algorithm, A star, were considered to be artificial intelligence because pathfinding was deemed to be something that required human intelligence. Nowadays, you really wouldn't consider those to be artificial intelligence. Those are just algorithms for pathfinding, right? And so there's a quote here: every time we figure out, we say, oh, that's just computation. It's no longer considered to be AI. So I want you to think about this and what people consider to be AI, especially in the news. A lot of things are considered to be AI, but I want you to really look into it and see if you would classify it yourself as AI, right? So AI is broad and subjective, its definition, and it depends on the perceived difficulty of the problem. And as soon as that problem or system is well understood or normalized, sometimes it ends up being labeled as just pure computation, right? So now what is machine learning versus artificial intelligence, right? So machine learning is a field that's a little bit more well-defined than artificial intelligence. I have two definitions here, right, that I'm going to share with you. Machine learning is the study of computer algorithms that improve automatically through experience. And machine learning is programming computers to optimize a performance criteria using example data or past experience. So we can see in the chart on the right that machine learning is classified as a subset of artificial intelligence, right? And what really separates machine learning from, artificial intelligence, and also from what is considered to just be regular computation, is that machine learning is really a set of algorithms that uses previous data to make information, or to make predictions or make decisions, right? And so the data determines how the predictions are made, right? Not just the input to your algorithm, right? So in a machine learning algorithm, the previous data you have fed the algorithm, as well as the input, classify what kind of output you get, right? But in a regular algorithm, the previous data doesn't matter, right? No matter what I send in, it will never update itself. The algorithm will never update itself and make a different output, right? Output will always be the same. And so that's really the biggest separation from machine learning versus regular computation algorithms, is that machine learning takes the previous data and builds on it and uses that in its output. Right? So different kinds of machine learning include supervised learning, right, where you train a model using a data set of input to label pairs, right? So everything is already labeled for you. Say, for example, you have a set of images of apples and bananas, and every single image is already classified as either an apple image or a banana image, right? Then in supervised learning, that is essentially what it is. You have your data set of inputs, which are the images, and they're already mapped to the labels, which is, right, apples and bananas, and then you just need to train a model to output the label based on the images that you give it, right? And so regression is essentially that you are trying to predict, or you're trying to output, a real continuous value. Say, for example, the apples and bananas is not obviously a regression, it's a classification task. But say, for example, you wanted to predict the price of a house based on a number of features that you gave about the house. That would be considered regression because you're trying to essentially predict a continuous value, right? There's also unsupervised learning, where you train a model using a data set of inputs that has no labels, and the goal is to find structures or patterns in the data. Some examples would be clustering, dimensionality reduction, anomaly detection. So something that's kind of used, right, a lot in unsupervised learning is that you're trying to kind of group different data points together, right? And you don't know the labels of the data points, but you're just essentially trying to figure out if you can group the data points in such a way that you can come up with meaningful groups to kind of learn something about the data, right? So clustering is something that's very commonly used, and that is unsupervised learning. Semi-supervised learning is where you train a model using a data set that has a small amount of labeled data and a large amount of unlabeled data, right? So something like fraud detection or image classification, you might have these examples, right? Fraud detection, you might not actually have a lot of examples of fraud because most of them go unnoticed, or you're unable to collect it, right? So let's say you have a model, you have a little bit of labeled data, you train your model on that labeled data, and then you have to apply it basically to a large amount of unlabeled data and try and learn again. And that's kind of semi-supervised learning. And then we have reinforcement learning, where you train a model to interact with an environment by predicting or taking actions right in that environment based on the state you feed the model, and also a specific reward function that is defined by the developer of the model, basically. So things like gaming bots or autonomous driving use generally reinforcement learning. So this is a scikit-learn algorithm cheat sheet. It kind of helps you decide on what kind of models you need to use for your task. It gives you a little start, and you can go through. I highly encourage you to check it out and go through it yourself. You can just search it up online, scikit-learn algorithm cheat sheet. Right. So at its core, mathematically, machine learning is an optimization problem. And as you recall, an optimization problem is a problem from calculus. We're essentially trying to find the critical points of a function, right? So how we treat it as an optimization problem is that we can conceptualize every single machine learning model as a function, which we define as f of theta, which takes in an input x, and it results in an output y, where the parameters are theta, and the parameters theta define the model that we're using, right? And so now that we've defined this function, we want to find the best function f theta of x, right? So we want to figure out the parameters that makes our function the best and outputs the closest values to the actual output, right? And how we do that is we define a loss function, right, L, that takes in as input theta, which are the parameters, right? So now we're defining a new function on top of our function or of our model, right, that measures the error a model's predictions are from the true target y, right? And so essentially to train this model, that just means finding the best parameters theta to minimize the loss function, right? So we kind of see that here. We take theta star, which equals the arguments of theta that minimize that loss function, right? So we're trying to find the minimum of the loss function because the loss function determines how well our model does on the data, right? And so this is kind of where it's kind of treated as an optimization problem because you're trying to find the critical point, which is the global minimum, right, of your loss function to create your model, which is a function as well, right? And we want our model to make accurate predictions or generalize on new unseen data, and we'll learn a little bit more about that as we go through the semester. Right. So we're going to go through a couple of the models that we covered. So one of the first and earliest models that has been used in machine learning and data science is linear regression, right? So linear regression, right, is an algorithm, as all machine learning algorithms are, for finding the best fitting hyperplane that predicts a value y, right, which is an element of the real numbers, given a set of one or more input variables, right? And so what we mean by hyperplane is basically based on the number of features you give it, the hyperplane is the plane with dimension n minus 1, right? So if you're providing a linear model with 9 features, then the hyperplane is of dimensionality 8, right? And so what we essentially do is we represent our data, right, as a matrix x, and we have the result vector y, right? So we let xi be the feature vector, and we let yi be the target value, for example, I. So you can see here on the bottom right-hand side, we have an example of our data set, right? Where the red row is essentially our first data point, right? Which is just those two numbers together. That's the vector that we're going to give to our model, right? And the y, the red box, is the output of our model, right? And so we can see that the model, essentially what we're doing is we're taking essentially the product, right, of our x and our weights, right, which is what we're trying to find here, which are the parameters, and we get our output y, right? So our model can be generalized to any number of features, right? So f theta, we can pass in any number of features, x1 all the way to xm, right? Where m is the number of features. And essentially all we're doing is a linear combination of the weights, right? w1 to wm, right? Because that's how many features we have, so that's how many weights we need. And we can come up with a linear hyperplane, essentially, right? That produces the output, right? And so we can kind of represent it in different ways. We can represent it, expand it out with the summation, but we can also commonly express it using linear algebra, where essentially we take the weights as a matrix, transpose it, and then we product it with x, and we add our bias term to get the output, right? And so that's kind of linear regression. And so using linear algebra, we can actually find a closed form solution for the weights, right, which are the parameters of our model. And we use it using ordinary least squares, right? And essentially we have this equation here which allows us to solve for the weights that we have for our linear regression model, right? And we don't need to use this closed form solution. We can use other methods as well to try and find the optimal parameters, right? Theta, of which basically is just the weights for this case. And we can kind of go from there. And we'll see that a lot of models actually do not have a closed form solution. And so there's a different way to kind of approach it, right? So some key takeaways for linear regression is that it's an algorithm for solving the best fit for a linear relationship, right? Between a set of given input values and a singular output value, right? And so we defined hypothesis class in the previous semester, but if you're unaware, hypothesis class is just essentially a set containing all of the models that we could theoretically be utilizing for our function, right? F of theta, right? And so using this essentially a model such as linear regression, we're essentially narrowing down the hypothesis class, which is the set of all models, by assuming the input-output relationship is linear, right? And so we're finding the best fit by minimizing the loss function that we've defined previously, right? So some advantages of linear regression, right, is that it's simple, it's fast, it's interpretable, and it serves as a baseline for regression, right? Disadvantages is that it underfits usually because of the assumption, right, that there is a linear relationship between the inputs, vectors, and the output, right? And so it's also sensitive to outliers in this case. So we'll go over logistic regression now, right? So we've talked about linear regression and how it produces a continuous value, right? Logistic regression is for classification, remember? So there's no continuous values. You either have like apple, banana, yes or no, right? There's no in between, right? And so how we actually do this is we kind of have a little bit of a weird way. We kind of go around it a weird way. So we have a normal linear regression model that we use, right? And then what we do is we apply the sigmoid function to the output of our linear regression model, right? And the sigmoid function, we're going to show it later, it squashes the values from negative infinity to go in between 0 and 1. And we'll see this in the next slide, right? And so essentially when it does this is we've created essentially, right, what is like a probability, we would say, from 0 to 1 of is this a part of our class or whatever, what we're classifying, right? And this is only a binary decision, right? And essentially what we do is we define a decision boundary. Say we set p equals 0.5, right? Then if the sigmoid function outputs a value greater than 0.5, we're going to label that to be a part of our class. If it's less than 0.5, we're going to label it to not be a part of our class, right? So that's kind of how we get around, doing this. Classification is really, we're just using a linear regression model and then applying a transformation function to map it to the values of 0 and 1, right? And that's kind of how it explains down here. How do we implement this? We derive a score using y hat equals w dot x plus b, and we plug this value into our sigmoid function. Okay, so you can see our sigmoid function graph here, right? It squashes the values into a probability between 0 and 1, right? And so it converts unbounded values into, right, the outcome that we're trying to get, which is this a part of our class or not, right? And so no matter what value we give the sigmoid function, it's going to squash it to between 0 and 1, right? And so normally 1 is that the input is a part of our class, and 0, the output, is not a part of our class, right? And this is only for binary decisions, right? Say, for example, if we're classifying an image, is an apple or not an apple, right? That's really the only thing that we can do here with this kind of logistic regression. All right. So now we're going to talk a little bit about neural networks, right, which we also covered last semester. So a neural network, right? So first, we're going to start off with the base components of it. There are units in a neural network, and each unit is called a neuron, right? And it is the single unit of computation in a neural network. Each neuron belongs to one layer, right? And every single layer in the neural network is fully connected to both its previous and next layer, meaning that the output of one neuron in layer 1 is given as input to all neurons in layer 2, right? That's what we mean by saying it's fully connected, right? And so essentially the kind of intuition behind a neural network, right, is that it approximates a target function, f of x, right? Where remember, f of x is the model that we're trying to create, right? So it's trying to approximate a target function, f of x, through a weighted sum of non-linear functions provided by the input, right? And so we use a set of non-linear functions here because, as you remember, when we briefly talked about linear regression, that linear regression assumes that there is a linear relationship between the inputs and the outputs, and neural networks make no such assumption, right? Meaning that neural networks theoretically can find nonlinear relationships, which is most common in real-world data, right? Not everything is usually described by a linear relationship between the inputs and the outputs. All right, so let's talk about neurons now, right? So we said it's a single unit of computation in a neural network, and we're going to define the output, right, of the neuron to be h of wb, right, where it's given the input x, and essentially it just is the dot product operation, and we add the bias, right? And so eventually after that, we use our activation function, right, that you can see here, and the activation function essentially takes the summation of all the previous outputs from the previous layer, and it produces a single output y, right? And you can see in the graph here how that works, right? So say, for example, all of the inputs might be a part of layer 1. That summation sign is representing a neuron in layer 2, right? And it takes in as input all of the values from the previous layers, right? And uses summation to kind of combine them together and sums them, adds a bias term, and then it uses the activation function to produce a final output y. And the activation function is really the key part here, right? The activation function can be anything, but we want it, like we said, to be a non-linear function. So that way we can kind of map, we can approximate non-linear functions using our neural network, right? And neurons are loosely based on actual neurological neurons. The first kind of neuron was called a perceptron, and so it was a neuron that used basically no bias term in the calculation of the output, and it had a step activation function. And so the step activation function was essentially that if the output of the summation was above a certain amount, it just returned that. If it was below a certain amount, it would return 0, right? And this was created by Frank Rosenblatt, and this kind of led to the entirety of neurons being developed. So how do neural networks actually learn, right? We have all of these weights and parameters in our neurons. We're passing all of this information forward. How do we update the neurons, right, to make sure that they're actually producing something meaningful, right? And we talk a lot about backpropagation and gradient descent last semester. Right, backpropagation is the essentially the technique to compute the gradient, the loss gradients, right, of our neural network with respect to all parameters using the chain rule, and it was introduced by Geoffrey Hinton in 1986. Essentially, the algorithm for backpropagation goes this way. We compute the forward pass and save intermediate results. So like we described in the previous slide, all of the neurons get as input all of the outputs from the previous neurons. It uses a summation to add them all together. It applies a bias term and produces its own output, right? Using the output, right, we compute the loss on the final output layer, right? Say, for example, in the neural network example on the top right, there's one output neuron, and let's say, right, the output neuron produces 1, but the expected value is 2, right? We use the loss, right? We're just going to use mean absolute loss, which would just be 1. And then using this loss, we're going to perform a backward pass on the previous layers using the chain rule, right? And we update the weights then based on the gradients, right? And you can kind of look through these GIFs here and see exactly how it's going through, right? And gradient descent, right, is just updating the parameters in the direction that reduces the loss using the computed gradients that we just calculated through backpropagation, right? Anybody have any questions so far? Like I said, if none of this is like, clicking, that's completely fine, because this is like assuming that you have prerequisite knowledge from the previous semester. So you guys, I definitely encourage you guys to go to our previous lectures on YouTube and go through all of them as well. All right. CNNs, right? So convolutional neural networks is another model we talked about. It's an architecture, right, of neural networks, obviously. And it utilizes what are called convolutional layers instead of regular layers, right? So a convolutional layer is just a layer where each neuron processes information from a limited set of the previous neurons, right? So it might only take in, so previously in the feed-forward neural networks, each layer was fully connected, right? A neuron took in as input all the outputs of the previous neurons, right? In a convolutional layer, that may not be the case, right? A neuron may take in only the input of 9 neurons in the previous layer, right? And so essentially what happens here is each neuron processes information from this limited set of the previous neurons, right? And it does this through a set of filters, also known as a kernel, right? And since CNNs are mostly used for image processing, image classification, a lot of that stuff, and we can kind of see through this GIF how it kind of generates information about the image, right? So essentially what it does, right, is it generates a filter, right, or a kernel, which is an array that slides, right, across the image, or we say convolves, across the image, or the previous layer's output to produce a feature map. And so the kernel or filter contains weights and a bias usually, and also an activation function, right? And so it produces what is called a feature map. And a feature map is essentially information on the input, right? And it produces information about the input image, right? Or the previous layer. And so applying the filter produces, a single output value, a real number for each sliding window, right? And so we combine all of these outputs to create our feature map, right? And so we can see in the GIF here how the feature map is created using the kernel, right? The kernel just basically slides across the input image, and it multiplies all of the values, and then it sums them together, right? And so there's no bias or activation function here, but normally a bias and an activation function would be used in a CNN, right? So we can see an example of a convolutional neural network, right? We take in the image, and then we have a filter that convolves around it, right? And so the first filter shape is a 3 by 3 by 3 filter, right? And then we have 64 kernels and 64 filters, right? So you remember each kernel produces one feature map. We have 64 kernels going across our image, right? So we're going to produce 64 feature maps. And so when we have 64 feature maps, then we have to create our second kernel, right? And our second kernel is 3 by 3 by 64, right? Because we have to convolve across the output of the previous layer. So the first layer produced 64 feature maps, right? So we have to have a kernel that has 3 by 3 by 64. And we can see here as we go throughout, we have the kernels changing in sizes, and eventually it produces a single filter, a single output where it's just essentially an array of 7 by 7 by 512, right? And essentially after this, we kind of have compressed the information of the image into this essentially this tensor, and we're just going to flatten it and send it through a regular feed-forward neural network, right? And when we send it through this feed-forward neural network, then we can kind of use the previous strategies that we talked about to either do classification or regression, right? So now we're going to talk about RNNs, which is the last model that we talked about. So recurrent neural networks are a type of neural network again, and is designed for sequential data rather than image data, right, like CNN. And so a recurrent neural network uses internal loops to store past information, which allows it to understand context and dependencies over time for tasks, right? So we can see here how the recurrent neural network differs from the feed-forward neural network. The recurrent neural network maintains a hidden state, which generates an output which feeds back to itself, right? And so essentially what happens here is you'll pass in multiple sequences, right? Or you have a sequence of data, right? And you'll pass in each data point of that sequence one at a time, right? Through your recurrent neural network. And then usually over time, your recurrent neural network will build up information about that sequence, and your final data point that you pass from your sequence into your neural network will generally be used as the final output, right, for that sequence, right? Whatever you want the output to be. And there are two common types of recurrent neural networks that a lot of people use. The first is a long short-term memory model, right, or LSTM, right? So it's a type of recurrent neural network, obviously, and it uses a very complex relatively to other types of RNNs. It uses what are called memory cells and gates to remember select information. So it's kind of selectively decides what kind of information about the previous inputs does it want to keep or does it want to forget, right? And so this kind of assists in learning long-term patterns in sequences because essentially it can decide to focus on the most important information, right? And we can see the graph of the LSTM cell. It takes in, right, the input, xi, right, from the previous layers, right? And it also has the hidden state, right, which is the weight that is the parameter of that neuron. And we also have the memory, right? So using the memory and the input given to it is going to calculate the new hidden state, which is, right, the new parameter for our neuron, as well as a new memory value, right, to be stored, to be used for future use, right, when we pass in another data point to our neural network. And then finally, we have gated recurrent unit models, right, or GRU models. So they're a more simplified version of RNNs compared to LSTM models. They use fewer gates than LSTMs to control what kind of memory to forget or to keep. And this makes them faster and easier to train, but they are a little bit less efficient in finding dependencies across longer ranges of data. But it's still pretty decent. And a lot of times GRUs are used in research and stuff like that for fast prototyping because the advantages of having an LSTM over a GRU is usually the performance is very, very small difference, right? And so that's why a lot of people prefer to use GRUs over LSTMs because the performance is not that different. It's only slightly worse on most occasions, but it's a lot faster to train and to use. But anyways, that is all for today. If you guys have questions, please feel free to ask and I'll be happy to answer. If you haven't already, make sure to sign in. And like I said before, I know there was a lot of content, in this 30-minute lecture or so. But I assure you that in the next lectures, we're going to go through everything more in depth, and we're going to focus on the applied aspect, right? How to implement these models, how to code in Python, how to set up your environments. So this was kind of just a review of the conceptual understanding of the machine learning models. And if you guys were not familiar with some of the concepts here, that is completely okay. I still encourage you to come to the next lecture where we'll go through everything more in depth throughout the rest of the semester. But anyways, that's it from me. Thank you guys so much for coming out, and I appreciate your attendance. Thank you.